The fundamental theorem part 2 is probably even more useful for us, and it's I would highlight this. Maybe put a heart next to it too. So the fundamental theorem part 2 says if f is a continuous function on the closed interval from a to b, then the definite integral of f from a to b is equal to capital F of b minus capital F of a, where capital F is any antiderivative of little f. That is a function such that big F prime is equal to small f. So what does this mean for us? This means if we know an antiderivative of little f, we can use it to find the definite integral. In our very first definite integral problem, we tried to solve this problem. The question here was find the area under the curve y equals x squared from 0 to 2. And if you remember, we took the limit of the sum, and it took about a page of notes to work that out. Now, it says, if I know any antiderivative of x squared, I can use that and evaluate that function at the two endpoints. So, do we know an antiderivative for x squared? Yes. 1/3 x cubed is an antiderivative of x squared. But I need to evaluate it at the endpoints, so I draw a vertical line and write my endpoints. This reminds me I still have to evaluate it. So it says use the upper limit first, and then minus f at the lower limit. And 2 cubed is 8. 8 divided by 3 is 8/3. 0 cubed is 0 times 1/3 is 0. And that is way faster than what we did previously using the Riemann sum limit of the sum definition. So this is amazing. Maybe put an arrow through the heart. All right, can we evaluate this next integral using the fundamental theorem part 2? Do a quick check. Is e to the x a continuous function from 1 to 3? Here's e to the x. Yes, it's continuous from 1 to 3. Do we know an antiderivative of e to the x? Yes, the antiderivative of e to the x is e to the x. So I can use the fundamental theorem, part 2, to evaluate this. And that's the exact value. If you want an estimate of this, you could just type it in your calculator. But that's it. We're done. This is a problem that we could not have done using the limit of the sum because that's an I. We could not have. Oh, I've already messed up my problem. There we go. That's better. So we would not have been able to find the sum of all of these. But it's very easy to find the antiderivative. All right, we already did one just like this. So I'm going to skip that one. Well, it's fast enough. I'll just do it. So that is the question. Find the definite integral from 0 to 1 of the function x squared from 0 to 1. I know an antiderivative. Hey, here's an antiderivative. Would this antiderivative also work? That's an antiderivative of that. Because if I take the derivative of the right-hand stuff, the derivative of 2 is 0. Is that okay? Can I do that? The answer is yes, because if I were to look at this, I would take my 1/3 times 1 cubed plus 2. There's my capital F of 1 minus 1/3 0 cubed plus 2. There's my capital F of 0. Notice it doesn't matter if we have a number here because you're just going to cancel that number out. What is this number? This number could have been a c, right? Since we can use any antiderivative, we always pick the one where c is 0, just because you don't want to make the mistake of messing this up. So this part right here is always going to cancel out when you do f of b minus f of a. So you might as well use the specific antiderivative where c is equal to 0. What about this next example? Do we know an antiderivative? Is this function a continuous function? Well, I don't like how this is written. Let's rewrite it. Let's rewrite it to look like this, because now I can more clearly see f of x is equal to 1 over x. Is 1 over x continuous everywhere? Well, no, it's not continuous when x equals 0. Luckily for us, that is not part of this interval that I'm talking about. Do I know an antiderivative of this, f of x? Yes. The antiderivative of f of x is the ln of x. So we have the ln of x from 3 to 6. The ln of 3 over 6, so it's ln of 6 minus the ln of 3. Using properties of the logs, we could rewrite that as ln of 6/3 or the ln of 2. And there you have it. What does this represent? This represents the area under the curve 1 over x from 3 to 6. Okay, we've got 2 more example problems for this section. This next one is a what's wrong with this kind of problem. Let's do a quick sketch of 1 over x squared. So here's 1 over x squared. And if we're looking for the area of 1 over x squared, well, everything's on the top half. It's all the y's are positive. So shouldn't the area be positive? So there's a question mark that I have. The next thing that I want to point out is that our lower and our upper values cross something that's undefined. So let's scroll back up. If f is a continuous function on the closed interval, well, f is not continuous at x equals 0. So at this point, this integral, this definite integral, cannot be defined or cannot be evaluated. So this one, the integral does not exist. Here's our last question, question number 30. And we want to determine the definite integral. Looking at this problem, we're thinking in terms of the fundamental theorem part 2. We're asking ourselves, is this a continuous function? And the answer is yes, it's a continuous function. It's just a 3u squared minus plus positive 3u minus 2u minus 2. It is just a parabola function, and a parabola is going to be continuous everywhere. Can we find an antiderivative function for this function? The answer to that is also yes. We can use the power rule to do this, but I'm going to combine like terms first. When I combine like terms, we've got 3u squared plus u minus 2 du. Notice in this problem, our variable is u. So is it okay that we have a different letter? Yes, that's fine. The u is our independent variable. It's doing exactly what x would do in this problem. So just because it's a different letter, don't let it bother you. Any other letters in this problem we would hold constant. So there aren't any other letters, just numbers. Now I can find an antiderivative of 3u squared plus u minus 2. I do not want to try to find an antiderivative of the original problem since it is a product and I don't really have a way yet to think about antiderivatives of products. But I do have a power rule. So I'm going to go with 3u to the plus 1 divided by the new power plus u squared divided by u minus 2u. I don't need plus c because remember we can pick any specific antiderivative we want, and I'm going to pick the one with c equals 0. So here I've got 2 cubed plus 2 squared over 2 minus 2 times 2. All of this is big F of 2, right? Minus negative 1 cubed plus negative 1 squared over 2 minus 2 times negative 1. All of that is f of negative 1. So from here we can just do the algebra, simplify this. 8 plus 2 minus 4 minus, careful with those parentheses, okay? Minus 1 plus 1/2 plus 2. Let's see if I can add here. I think I'll go with a not 14 because I can't add apparently. 6 minus what's in here? That 3/2. 6 minus 3/2. 6 is 12/2. Kind of looks like 9/2 to me. If I can add. Don't know. And that is Fundamental Theorem Part 1 and Part 2.